1.1 power functions. So any polynomial expression in this form, anxn plus an minus 1 x to the power of n minus 1 plus an minus 2 x power n minus 2. Dot dot means it's continuous. The power is decreasing by 1, the power of x. And this is the coefficient. So then x power 3, x power 2, x, and here is the constant number. All of an to a0, they are constant numbers, and the power can decrease. So the highest power is n. We call this one polynomial expression. So the power here, in order for this expression to be polynomial, it should be whole number like 1, 2, 3, 4, and so on, right? This will be your degree. Just make note, you cannot have the power to be negative. To n cannot be a negative number, or it cannot be a fraction, right? Like 1 or 2, or any decimal. N cannot be these ones, just whole number. X is variable. An, coefficient of the highest power, is your leading coefficient. And a0, this is the last one that you have here, is constant. Now we're looking at an example here to understand that better. Let's say here ax power n, the degree gonna be n because the highest power of the x is n, and the leading coefficient is a. In this example, the degree's highest power is 3. And the leading coefficient is the coefficient of the highest power is 7. And the constant, of course, is -7. It's here. Okay. So we know this parent function for linear, for quadratic, cubic, quartic is x power 4, contic is x power 5. You want to graph it and just say something about these properties. Everyone know how to graph a linear. Just a reminder, we could have 2 points or 3 point if you want. Let's say -1 is going to be -1. The x is -1, the y is going to be -1. And x is 0, the y is 0. And the x is 1, y is 1. This 3 point is enough for me to graph it. 0, 0, 1, 1, -1, -1, and you connect it. Everyone knows this is the graph of y equal x. The highest power is 1. That's why the degree is 1. The leading coefficient is +1. X power 2, we have 3 point again, and the x is -1. -1 to the power of 2 is 1. X 0, 0 to the power of 2 is 0. 1, 1 to the power of 2 is 1. We have 3 points, 0, 0, 1, 1, -1, 1. So I connect these 3 points, and this is my graph. So it's quadratic. The highest power of the x is 2, so the degree is 2. The leading coefficient is +1. Now here is the graph of cubic. So cubic, again, I can put 3 points here, x, y, -1, 0, 1. -1 to the power of 3 is -1, 0 to the power of 3 is 0, 1 to the power of 3 is 1. Okay, to graph that, I know this. What do we have? It's not going to be a straight line. Cubic is curved. Remember that is curved up here, and here is curved down. Okay, so this is cubic. The highest degree is 3, so the degree is 3. The highest power is 3 degrees, and the leading coefficient is +1. That's positive. Also, x power 4, the same manner we did x power 2, we can do that. -1 to the power of 4 is 1. 0 to the power of 4 is 0. 1 to the power of 4 is 1. 0, 0, 1, 1, negative 1, 1. This is look like that. And this is correct. The highest power of x is 4, so the degree is 4. The leading coefficient is positive 1. The quantic, the same thing. I did x, y, negative 1 to the power of 5 is negative 1. 0 to the power of 5 is 0. 1 to the power of 5 is 1. Again, we have these 3 points. So this is 1, 1. This is negative 1, 1. Now you have to curve. So it's not going to be straight down. You have to curve it up, curve it down. As you see, x power 5 and x power 3 has the same shape. I expected that x power 7, all of the odd power have the same shapes. It's going to make it smaller, so perhaps you can see this all together. See, the quadratic is the same as quartic. Power 2, power 4. There are even powers. Just look like that. The odd power look like each other. So these are the points that I would like to take in. Here is the y equal to negative 5. Look at that. Y equal to negative 5. What does it mean? Y equal to the negative 5, it is saying that the y is constant no matter what's the value of the x. The y is always 5. So if you want to do it, if the x is, let's say, 0, of course, the y is always negative 5. If the x is 1, the y is negative 5. If the x is 2, the y is negative 5. You can really draw that easily. So 0, let's say 5, 1 is 5, 2 is, sorry, this is negative 5. I have to do the negative. Negative 5, let's say this is negative 5, this. As you see, this is the line, right? This is a straight horizontal line. So the degree, we don't have x here, right? This is the same as saying negative 5 x to the power of 0, because I know x to the power of 0 is 1, kind of this is equal to negative 5. But the highest power of the x 0, that's why the degree here, degree is 0. Okay, so for the domain and range, I'm going to do the domain and range for a couple of that. So let's say for x, as you see, all of the positive value of the x is covered here. This negative value of the x is covered here. So for this, we say domain. Domain is XER, x all real values. And for the range is YER. See, this part is covering all of the positive value of the y, and this part is covering all of the negative value of the y. So it's just y belong to real number. For x power 2 here, for domain, we have x belong to a real number. This part, see, this is covering the positive value of the x's, and this part is covering the negative value of the x's, and this continues forever. So there is no restriction for domain. For the range, on the other hand, the range, as you see, I'm going to show it different color. The y values is of this part covering the positive y value, and this part covering also the positive value of that. We don't have any negative value for r. That's why the for y. It's going to be YER. There's a restriction, right? The y is always positive. Y greater equal than 0. So these are the domain and range. You know, for this one, for the cubic, you can say the same. This part is positive, and here's negative value is covering all of the x-axis. There is no restriction for y as well. For x power 2, because it's really look like x power 4 and x power are the same. They have the same domain and range. And also x power 5 going to be the same as x power 3 for domain and range, which is there is no restriction for x and y. Clear that. Now we're going to the end behavior. Looking at this example, I want to see, written in this graph, what happened if you x go to positive infinity, x go to a very big number, what's going to happen to the y? So for positive infinity, I have to look here, right? At this end, I need to look at this end. If this continues, x go very big, of course the y go up. It become positive, right? So y go to positive value. Now I want to see what happened when the x go to negative infinity. For that one, I need to look at this end because the x of negative infinity is happening here. When the x is negative, the y is negative, right? So the y go to negative infinity, negative big number. Okay, now the next picture, I'm gonna do the domain the end behavior again. When x go to positive infinity, I have to look at this end because the x positive is here. So it's go up, the y is positive, right? Then the y go to positive infinity. Also, I want to see what happens when the x go to negative infinity. What happened to the y? I have to look at this end. See, when the x is negative, my y is positive, right? So it's going to be positive infinity. So these are the ends behavior. Okay, these are the end behavior. Now the symmetricity. So when we have a line symmetry, anything in this shape, right, that is symmetric with respect to a line. The line of the symmetry here is y-axis. See this here? If I take any point here and reflect it with respect to the y-axis, I get the other half of my graph, right? So any point you reflect, you get the other part. Reflect with respect to this line, it's going to be what? You will get the other half. That's why it's a line of a symmetry. It's like this one. Any point you reflect with respect to this line, you get the other half of your graph. This is the line of symmetry. Now, point symmetry. At the other hand, the point symmetry, an example going to be like this. Okay, if I take any point in this part, connect it to this, and continue the same way, I get the other part of my graph. Any point you choose here, you connect it to this 0, 0 point, you continue the same distance, you get the other half of a graph. So this is symmetric with respect to 0, 0. But it has a point of the symmetry. Here, the point of symmetry is 0, 0. This is like this one, the point of the symmetry here is this point, and when you reflect respect to this one, you get the other half of your graph. This is a point of symmetry. So this is that. Now, according to this, I want to see if this graph is even or odd degree. If you go back to the previous pages, we did something like that. Anything like that, of course, is even degree, right? So I know this is even degree. But how about this is even degree, right? How about the sign of the leading coefficient? I know y is equal to x power 2 is look like that. The end behavior is quadrant 1 and quadrant 2. And y is equal to negative x power 2. The end gonna be here and here. Of course, when the leading coefficient negative is happening, so the leading coefficient gonna be here negative. Domain and range. For the domain, see this part is covering all positive value of the x, and this part is covering all negative value of the x. There is no restriction. And for y value, the y value is just negative. So this part is covering all negative value, this part covering again all negative value. As you see, your y is just negative. So it's y or y less than or equal to 0. Also about the symmetricity, this is a line of the symmetry. Let's just talk about the end behavior. For x go to positive infinity, I want to see what happened to the y. X positive infinity is here, so I have to look at this end. When the x is positive, the y is what? Negative, so it's going to be negative infinity. Also, when the x go to negative infinity, I want to see how does the y works. See, for negative x is negative infinity, I have to look here. X is negative infinity, y gonna be negative as well. So this is the end behavior here.